Pre-calculus students, welcome to your 3.3 notes. We're going to look at properties of logarithms today. Some of it will be review, some of it may be a little new to some of you, but in the end we're going to be able to learn these properties so we can solve some logarithms. So let's get started here. First of all, the change of base formula. You can see it written here in the box. It's for a, b, and x being positive numbers with a and b not equal to 1. You can rewrite something like log base a of x. You can separate it and choose your own base. They've got it written three different ways here. Log base b of x divided by log base b of a. Log base 10 of x divided by log base 10 of a. And then natural log of x over natural log of a. Those are all equivalent equations. The reason we need that change of base formula, it's actually pretty simple. For one reason, it allows us to choose a base that we can work with, that works for both numbers. And in other cases, it just simply allows us to use our calculator to find approximations for values. Three other properties are listed down here, the product, quotient, and power properties. We're going to look at all of these. I'll let you guys read through this, but we'll look at all of them as we get through the different problems we're going to look at today. So let's get rolling here. Let's rewrite the log base 7 of x as a ratio of common logs and a ratio of natural logs. So this is a pretty fast problem. It's just using the change of base formula. If we're using common log, that means your log base 10. So I'm just going to write it as log of x divided by the log of 7. That's it. And then for part B, instead of using log base 10, we'll use the natural log. So we have the natural log of x divided by the natural log of 7. So we could choose any base we wanted. In this case we chose base 10, and this one we chose base e. Alright, number 2, we're going to use the change of base formula to approximate values or to solve for exact values. And actually on number 2, when you think about it, 8 and 32 is not a power of 8, but they're both powers of 2. So I'm going to choose base 2 on this one. So I'm going to do log base 2 of 32 divided by log base 2 of 8. Again, you can choose any base you want. The advantage in this case of base 2 is that 2 to the 5th power is 32 and 2 to the 3rd power is 8. So we know that the log base 8 of 32 is exactly 5/3. Now on the second one here, we can't choose a number that's going to go evenly into both. Unfortunately, 5 is prime, 17 is prime. There's no way we're going to be able to simplify those to exact values. So let me show you two ways we could do this. If we do just simply change a base formula in the traditional sense on our calculators, we do log of 17 divided by the log of 5. And by the way, I'm choosing base 10, but we could have chosen natural log just as easily, and that would work and give us an answer like that. Some of you may prefer to go this route though. If you hit alpha and F2 and you see option 5 here says log base, and then you can type it in so it'll look just like what the problem looks like, almost making the change of base formula somewhat obsolete but still valuable for exact values. So in any case, we got about 1.76 whichever method we used. Alright, we're going to do some more simplification using other properties here. So let's see. The first one says find the exact value of the logarithm expression log base 7 of 1/49th. Well, I think you guys probably know this, but log 1/49th is just 7 to the negative 2 power. So the log base 7 is 7 to negative 2. We could use our inverse property we learned yesterday and just know that that's negative 2. There are other ways to think about that one, but that's a good one. Alright, number 4. Here's what I'm looking at on number 4. I want that exponent to move out front. So I'm going to rewrite this thing as 3.7 times the log base 3 of 9. That's one of the great things about logarithms. Our exponents we can move to be coefficients, or sometimes it's more important for us to take a coefficient and move it to be an exponent depending on what we're trying to do. In this case, going this route gives us a pretty quick result. Log base 3 of 9 of course is 2, and then 3.7 times 2 is 7.4. All right, number 5. What I would think about this here is we've got 5 times the natural log of e to the 7. Well, the natural log of e to the 7 is 7 minus 7 times natural log of e to the 4th. That's just 4. So we've got 35 minus 28. That's exactly 7. All right, and then number 6. One thing we might want to do, this notation here with the radical symbol might mess with some of you. So let's rewrite it as an exponent. So this is negative 2 times the natural log of e to the 7/3 power. Remember, your root goes in the denominator, your power goes in the numerator. So negative 2 natural log of e to the 7/3 is the equivalent of what you see here. And now we can think of it as, okay, well, that's just simply negative 2 times 7/3, which would give us negative 14/3. All right, as we move forward here, what we're going to be focusing on now is expanding or condensing logarithms and learn our properties that work with that. So we're going to use the properties to, on this page, we're going to expand to a sum, difference, or a constant multiple. And I'll talk about that when we get there. We'll see that on number 8. But first, on number 7, log base 7 of x over y. So when you have this set up, log base 7 of x divided by y, we can rewrite that to be log base 7 of x, and since it's division, we change it to subtraction, minus log base 7 of y. And these properties that I'm using here are all on the first slide. You can step back and take a look at those if you need to. But the one we're using here is called the quotient property. Kind of makes sense since it's division, right? Okay, on number 8, we got the natural log of the 7th root of k. Again, one thing that might help some of you is to think of this as the natural log of k to the 1/7, instead of thinking of it as the 7th root, because 7th root can kind of mess with our heads a little bit. And then we have that power property, which says we can take our exponent and move it out front. And that is actually called the power property. It's the third one on that list on the first page. And this would be 1/7 the natural log of k. Now, this isn't doing a whole lot of work. It's just simply moving the exponent to be a coefficient. I'm doing that because the instructions say to expand, and it says a sum, a difference. Okay, those don't apply. Or a constant multiple of logarithms. Here's our constant multiple. That means we're taking a logarithm times a constant. So we need to get all those exponents out to be coefficients. All right, and then one more expansion problem. I'm going to do this one step at a time, and then we'll do a little more simplification after that. But we have two terms that are being multiplied and one that's divided. So I'm going to break this into 3 parts. Log base 9 of x squared plus log base 9 of y. And then we have that square root of z in the denominator. So that's minus log base 9 of the square root of z. Now again, the multiplication led to addition, the division led to subtraction. Okay, now the only other thing we need to deal with here is a couple of these terms have exponents, so we're going to rewrite those. So the first one, instead of log base 9 of x squared, we're going to bring that 2 out in front. So we've got 2 times the log base 9 of x plus the log base 9 of y minus, and again I have an exponent here in disguise as a square root symbol, so minus 1/2 log base 9 of z. On to the last slide. So on 10 through 13, we're going to do essentially the opposite of what we were just doing on the previous slide where we were expanding. Now we're going to condense. So we're going to take our addition and subtraction and condense it down to hopefully single logarithms. So here we have the natural log of x plus the natural log of 7. We can just rewrite that as the natural log of 7x. So there you go, and maybe 7x in parentheses would be good just to make sure that people understand the natural logs applying to both. In this case, we took an addition problem and changed it into a product of the terms. All right, so here we go, number 11. This time we've been taking our exponents and moving them to be coefficients, we're going to move the opposite way this time and move our coefficient right out here to be an exponent. And I'm going to go ahead and do kind of two things at once here. It's the log of x plus y to the 3/5 power. But when you think about it, the 3/5 power, we could rewrite it this way. I'm going to do that as a root, where it's the 5th root raised to the 3rd power. And that's the preferred way to write those on that kind of problem, is to go ahead and change them into a radical form. Very cool, isn't it? Okay, I thought that was funny. All right, number 12. 3 times the log base 3 of x plus 5 times the log base 3 of y minus 7 log base 3 of z. Folks, on this, each time we're going to move those coefficients to be exponents. And then we're going to rewrite it. We've got addition, we've got subtraction. All of these are base 3, so I can condense this down to this. Log base 3 of, well, I'm going to have x to the 3rd in the numerator. Also in the numerator, I'm going to have y to the 5th. And then in the denominator, I'll have z to the 7th. One thing I probably should point out, in the previous problem, it may have been tempting to try to change that x plus y to be x times y. But remember, when we can change addition to multiplication, it's when you have a term like the log of y minus the log of z, things like that, we can change to addition. So if this on number 11 said the log of x plus the log of y, then yeah, we could go ahead and change that to be a multiplication problem. But you can't like use the distributive property here and say, oh, the log of x plus y is the log of x plus the log of y. That's not true at all. The log of x plus the log of y would be the log of x times y, or xy. So you can't really do anything with this other than just rewrite it like we already did. All right, finally, number 13, -3 natural log of 3x. What I'm going to do is move that coefficient to be an exponent, and I'm going to from there go ahead, I'll apply the -3 power. So 3 to the -3rd would be 1/27th, and x to the -3rd is x to the -3rd. I'll just go ahead and put it in the denominator as x to the +3, and we've got it. All right, take a deep breath and go get to work on your assignment for 3-3. You guys have a spectacular day, and I will see you